I don't know how long I'm going to be able to last, but let me at least do a little bit of the PSR story for you. So this is the third leg of the where do rewards come from, what are actions about, and where do states come from. And I'm going to now talk about states. And there are lots of people who think about states. State estimation is a very active area of research in all kinds of fields, control theory, operations research, and so on, including machine learning. But we have a different perspective here, and I'm going to present to you sort of the perspective in the purest form. How many of you have heard me or somebody else talk about PSRs before? Just maybe 3 or 4. Yeah, it'll be pretty review for you guys. But I'm mainly I'm going to do what I want to communicate to you is what's different about PSRs, how it's, what's the foundational ideas in there, and some of the starting points. And if you want to dive into the latest stuff, the very latest stuff is being done by Jeff Gordon and Brian Boots at CMU. Very exciting stuff is coming out of their group that extends PSRs, and I won't get a chance to talk about it. I'm going to talk about the foundational ideas behind PSRs. So the fact is, most problems are partially observable. We didn't talk about partial observability at all, right? We talked about Markov decision processes almost exclusively. And Markov decision processes are more applicable than people think, because it's not just the case, let me remind you, that the observation is state, but that the more general story is that any state estimation procedure that captures a sufficient statistic of history, that captures all the information there is in history relevant to predictions about the future, makes the problem Markov. And so we talked about kth order Markov, where the last k observations make it Markov. We talked about what happens in practice, of course, is people go to a real situation and they make up features of history, which they maintain and treat as estimates of state. And that's the most common way of doing this. But we're going to look at more principled approaches than that one. There are basically 2 big classes of approaches. I mean, to call the PSR story big is probably not fair. The biggest approach is the whole latent variable graphical models, POMDPs, HMMs, hierarchical graphical models. It's all about when they deal with time, which is not very often. Of course, HMMs deal with time. When they deal with time at all, they are, in effect, doing some kind of state estimation. And we're going to talk about a very different way of thinking about estimating state, which, again, is called predictive state representation. What's the intuition behind it? The intuition behind it is that, let me contrast the 2 approaches. The 2 approaches would be, the latent variable approach would be the approach that says the world is composed of objects and relations between objects. So yes, I can't observe objects directly. I get some pixel array imagery, but I'm going to compute distributions over posterior distributions over objects and relations between objects. And then I'm going to use that as my representation of the world, and then build models that predict those things. That's the usual view. That's the 99% view, right? Here's the other view. The other view is, I don't think about the world as, belief states or distributions over where tables are and where chairs are and where doors are and stuff like that. Instead, the way I capture my state is predictions about ways of behaving. So my state right now is that if I had to get home, which is in Ann Arbor, I could get there in 5 hours. That if I pick up the phone and call this number, I expect to hear a certain voice. That, I can only move so many feet before bumping into something. Back, right? I have all these predictions that I can make. Now, of course, there are infinite number of predictions I can make. And of course, the goal of a model is to be able to let you make these predictions. And POMDP models and latent variable models are models that allow you to make these predictions. But the novel idea here is that these predictions themselves could be representations of state. So All models allow you to make predictions. That's not what distinguishes models. Modeling is about making predictions. In this context of dynamical systems, right? We're talking about dynamical systems. Modeling a dynamical system is to make predictions, what observations we'll see when we act in certain ways, right? That's what models are about. Markov MDP model was about that. So all models make predictions. The novel idea here is the predictions themselves will serve as state, will serve as what you will make other predictions on the basis of. And the nice thing about predictions, as opposed to latent variables, is predictions are realized or failed. That is, we get direct experience in the world about our predictions. While latent variables, we don't get to ever directly see. Right? So that's the insight. The insight is we're going to use predictions as state. I'll be making very precise in a few minutes. We're going to make predictions as state and use them to make other predictions. I mean, one thing you'd be thinking of is we can make so many predictions. How many predictions do we need to keep in order to be able to make all the other predictions? Turns out, not more than the number of states you would keep if you were to do belief state estimation. So it's not, you might think that one of the reasons why you want to do latent variable models is that it's very parsimonious. Now, I don't have a proof that it's just as parsimonious in PSRs, except in particular settings. In particular settings, I will prove to you, in fact, that PSRs can be more compact than latent variable models. So that's the idea. Does it sound bizarre? I don't know. Who thinks it's bizarre? That predictions themselves can be a representation of your current situation. I mean, in one way it makes sense, right? If I can get the right degrees of freedom in these predictions, then I've captured my situation and I should be able to make other predictions. Now, the tricky part is, of course, I have to maintain these predictions. Okay, so let's dive into it. All right. Let's look at two classes of dynamical systems. Uncontrolled dynamical systems, which is different from what we've talked about, but many people care about uncontrolled dynamical systems. People who do speech understanding or text processing or time series predictions are doing uncontrolled dynamical systems. There are no actions. There's just some environment spitting out sequences of observations. And you want to build a model that predicts distributions over future observation sequences. So that's the usual, any sort of time series kind of problem is an uncontrolled dynamical system. But of course, we're interested in controlled dynamical systems, but the uncontrolled dynamical system is just a special case where there are no actions. That's why it's called uncontrolled dynamical system. Here, the agent puts in actions and gets observations. So it's action observation sequences as opposed to alternating action observation as opposed to just observation. So here is, while PSRs have gone beyond these restrictions, it's easiest to explain PSRs in this setting, which is a setting of discrete time, finite observations, and finite number of actions, or the uncontrolled setting, which is, of course, a special case. So we're going to do it in this setting. All right? So we're going to predict the future, right? Everything is about predicting the future. Modeling is about predicting the future. So what's a future? A future in the uncontrolled setting is just the sequence of observations you might see. It's a specific sequence of observations. A future so what's a prediction about a future? So let's make some notation. So a future, which we call T, I don't know why we call it T. I guess we call it T because we think of them as tests. But we'll come to tests in a minute. So you have some sequence of observations, K observations. In a control system, it'll be K action observation pairs. So what's a prediction for a future? A prediction of future T is just the probability of that future. And the control system is the probability of that future given that sequence of actions. So it's a controlled, it's a conditional prediction. Predicting the future observations, conditioned on the future actions, right? Because obviously what I do will impact what I see. Okay, so now let's think of an exhaustive, enumerative, extensional definition of a model. The extensional definition of a model is this infinite vector. is the prediction of all possible futures from the beginning of time. So length 1 future, length 1 future, length 1 future, length 2 futures, length 3 futures, length 4 futures. Of course, they get exponentially larger as you look at larger lengths. The point is, if I give you this vector, I've defined the system completely. Right? A system is a generator of observation sequences in the future. And so this is a model. Now, this is a very poor model. It's infinite in size. So this is not the model we're going to use. But any model of a dynamical system should be able to produce this as output. Right? It should be able to predict the probability of any length future. Now, of course, there's lots of constraints in this vector. Right? These aren't arbitrary numbers. They're all probabilities, but there are more constraints. Right? The probability of marginalizing the first prediction, there are constraints between length 2 prediction and length 1 prediction, the length 3 prediction, length 2 prediction, and so on. So there are all kinds of constraints in here. So obviously, this is not a compact representation. Okay. Nope, doesn't work. Okay. So now let me build up to PSRs in a couple of steps. So now let me take that vector, which was from the null history, from the beginning of time. So T1 is a sequence from the beginning of time. T2 is a sequence from the beginning of time. Again, just to be clear, right? What are these columns? These columns are different length futures. So suppose there are 2 observations. Let's do the uncontrolled setting. Just 0 and 1 are the observations. So this is 0, this is 1, this is 0, 0, 0, 1, 1, 0, 1, or length 2, or length 3, or length 4 bits, or length 5 bits, and so on. That's what this is. Okay, but I want to make predictions not just from the starting point, but from all possible histories. So all possible futures, all possible pasts. All length 0 past, length 1 past, length 2 pasts, length 3 past, length 4 past. So I've taken this stochastic, this prediction vector, or a system dynamics vector, and converted it into a system dynamics matrix. Now, again, what do I want? What is P of Ti given Hj? Is the conditional probability in the uncontrolled system of the sequence of observations in Ti given that the history was this sequence of observations. Right? So it's the obvious thing. Is the prediction of that future given that history? It's just a number between 0 and 1. It's a probability. And in a controlled system, it will be similar, except it will also condition on the future actions. So this is, again, I've taken that one vector, which was a sufficient representation of a dynamical system, and made it bigger. Took a 1 by infinity vector and made it infinity by infinity matrix. OK. There is a payoff for this, you'll see. Except I can't use this anymore. OK. Oh, it's not full screen. I didn't notice that. Good point. That was it. That was it. OK, good. All right. So we're looking at a system dynamics matrix. All rows are uniquely determined by the first row. OK, now, here's the idea. Here's the crucial idea. Notice we have made no assumptions about the system whatsoever. No stationarity assumptions. No assumptions except discrete time, interaction, and finite number of observations, finite number of actions. If you are comfortable thinking about uncontrolled systems, think about uncontrolled systems. It doesn't matter. OK. So this matrix will have some rank. Now, it could be infinite, but it'll have some rank. Let that rank be n, capital N. We'll call that the linear dimension of this dynamical system. And this rank will play an important role in the development of what I'm going to talk about next. So again, the crucial point is any model must be able to generate this matrix. Right? That's what a model should do. A perfect model should generate this matrix. OK. Now, if the rank is n, it means there are n linearly independent columns. Of course, there are n linearly independent rows as well. But let's look at columns. And let's, for ease of drawing, imagine these n columns as being linearly independent. Let's give them special names, Q1 to Qn. Now, these are not unique, right? There are many possible n linearly independent columns. But let's pick one. OK. Here's the point. Here's the crucial point. If for any history, h, I give you these n numbers, then I can make the prediction for any other future from just these n numbers. Right? Because this column is linearly dependent on these columns. So any column is a particular weighted combination of these n numbers. So if I give you these n numbers, I have a sufficient statistic of history or state. What I haven't told you is how to maintain these n numbers. But the crucial thing, if you don't get this part, all the rest is out of the window. So make sure you get this. Ask whatever you need to ask. The claim is, again, that for any history h, if I give you these n numbers, I can make any other prediction about that same history from just those n numbers as a weighted sum. In other words, no matter how long this history is, this history could be 10,000 steps long, these n numbers are sufficient. And it comes from the fact that n is a rank of this matrix, and that these are n linearly independent columns. OK. Now, how do we predict that number? We predict that number by asking, what is the test here? It's t. What is the future here? T. So P of t given h is P of q, which is this vector of n numbers, so vector transpose. So inner product, and the weight vector is m sub t. So there's a separate weight vector for every future we want to make a prediction of. So this m sub t, which is n numbers, will take these n numbers, which is I've written in a vector form, and compute this number. So it's taking the inner product. OK? Note, here's the crucial thing. Note that m sub t, the weights that produce this prediction, is independent of h. So the only dependence on h is in this prediction vector. Right? Because, of course, the same m sub t produces this entire column from these n columns. So the weights are not a function of history. Yeah? OK. So the prediction for any test is a linear combination of predictions. Oh, we call them the core tests. So these are what these futures or tests are called core tests, because their predictions will be our representation of state. OK, so, well, the question is n finite for any interesting system? Right? That's the next question. Suppose you have a dynamical system. How big is n? Because after all, n could be very, very large, and then they wouldn't be interesting. So let's take kth order Markov processes. Yes?
Sorry, I think I'm a little bit confused on that. The rank n is only for that little section of the T.
Rank n is of this entire infinite by infinite matrix. Entire matrix. It has some rank, whatever it is. It could be infinite. But let's say it's n and finite. We'll talk about what classes of systems have finite rank. Turns out far more interesting than you might think. OK? So now let me show you what the rank that corresponds to a kth order Markov process is. Remember what's a kth order Markov process. A kth order Markov process is a process in which the predictions of the future, given any history, depend on just the last k observations. Right? That's what it means for a kth order Markov, for a process to be a kth order Markov process, is the last k observations are a sufficient statistic of history. That is, how many different rows can there be here? Somebody help me answer this. How many different rows can be here? By the way, sorry, I meant nth order Markov process, but it doesn't matter. It reminds me of a math joke. I took a math class at UMass. You might have taken it. Rosenberg, not Rosenberg, somebody else. Took 2 or 3 math classes, and every year with that same guy, he would start the first lecture by this joke. It's just a terrible math joke. Pick a number A, call it B, and you won't get it. I thought it was hilarious.
No, I didn't know that.
You always start the joke with that. We're looking at nth order Markov process, nth order. So let's imagine that the total number of length n observations is k. So if there are 2 observations, then it's 2 to the n, k is 2 to the n. If there are m observations, it's m to the n. Okay, but what's the rank of this matrix? And why? Work to the logic of this. What's the rank of this matrix? Notice immediately a fact. The rank of a matrix is no more than the number of independent rows or independent columns. So what's the rank of this matrix? K, right? Because there are at most k different length n histories, and any 2 histories that have the same last n observations will have exactly the same rows. So in fact, something stronger we can say. There are exactly k unique rows, because every history that shares the last n observations with a different history will have the same predictions. That's what it means for a kth order Markov process. So the rank of this matrix is no more than the number of possible histories number of possible paths you have to remember. Okay. So that was that. Oh, I didn't talk about model parameters. How do you make predictions of the future? I guess I did talk a little bit about it. Let me wait till So all kth order or all k history Markov models are dynamical systems of linear dimension less than or equal to k. Okay, I'm going to prove to you that there exist dynamical systems of linear dimension n which cannot be modeled by any finite order Markov model. In fact, let me make up a system which has rank exactly 2 and which cannot be modeled by any finite order Markov process. Imagine that the very first state can be one of 2 states. If it's state A, then the world goes like this, and if it's state B, the world goes like this. These observations are all the same set. So given any history, you can't tell which world you're in except by going back all the way to the beginning of time. So you have to remember something arbitrarily far back in the past. Right? Trivial construction. But the point is, every kth order Markov process is small rank, has rank k basically. Every k history Markov process has rank k basically. Right? While there are very short rank systems, linear dimension systems that are not kth order Markov for any small k. Right? Okay, let's keep going. Oh, this is now I'm going to show you a result about POMDP. So I think this diagram is sort of familiar to most of you, but let me say a little bit more about it. So think of HMMs. HMMs have a sequence of states and sequence of observations that hang off them. But now these are POMDPs because there are actions as well. But ignore the actions if you like. So in fact, this is the standard unstructured representation of states. Sorry, not this. This is a standard unstructured representation of models. What's the state in this model, by the way? Who remembers what's the definition of state? What's the sufficient statistic of history in HMMs, POMDPs? Somebody wanted to say something. Go for it. What's the definition of state in an HMM or a POMDP? It's just a posterior distribution of underlying states, right? So you take your sequence of observations and you maintain a posterior distribution over the possible states, the world, latent states that you never get to observe the world could be in. So the representation of state in a POMDP or an HMM is n-dimensional probability vectors if the number of underlying hidden states is n. right? The belief state in an HMM or a POMDP is n-dimensional if the number of underlying states is n. What I'm going to show you is that the maximal rank of any POMDP system with n underlying states is n. Okay, that's what I'm going to show you. I'm going to show you that the maximal rank of any underlying HMM or POMDP system, doesn't matter which one, right? If there are n underlying states, then the maximal rank is n. That's what I'm going to show you. Okay, so that's the sort of the surprising result, right? Most people would say, yeah, sure, you can keep predictions, but you have to keep a heck of a lot more. That POMDPs would be much more robust. Now, to be fair, I'm making an unfair comparison in the sense that I'm not allowing any structure in POMDPs, right? I'm looking at unstructured setting, but I'm also going to compare with unstructured PSRs. There could be structured PSRs, which we are not going to get into. So I'm comparing apples to apples, but you can argue that this is not an interesting apple, but that would be a different story. But on the other hand, HMMs are used quite a lot, right? And POMDPs are used quite a lot. This is the alternative, right? Or this is the standard method. PSRs are an alternative. This is a standard method. I mean, there are really three methods. Keep history. That's the kth order Markov. Do POMDPs. These are the two most popular methods. And then the PSRs are an interesting method because they look to the future to represent the state. So you'll see. Okay, so we did all that. Now let me remind you of how belief state updates work. So the belief state denoted B, again, remember this is n-dimensional vector, on some history HAO. So I've taken H, which is my current belief state, and I've taken action A and seen observation O, so I have to update my belief state. And basically it's this normalized linear update. And if I want to make predictions about the future, given any history, I can make that from the belief state of that history. That has to be the case because I'm arguing the belief state is a sufficient representation of the history, which means I can make the prediction for any future, T, given history, in this sort of linear form. So if I want to make a prediction about A1, the future A1, O1, AK, OK, I multiply with the transition matrix corresponding to that action, the observation matrix corresponding to that observation, and I just do this. OK. So here's the point. So now let's look at the corresponding, this POMDP will generate a system dynamics matrix. So let's imagine this is a system dynamics matrix. So here's the point. The point is, OK, let's see what it shows up. OK, so here are the predictions. Oops, here are the predictions. P of t given T1 given H0, that's system dynamics matrix. Recall I just showed you that the predictions are linear functions of belief state. So I've replaced the predictions by that linear function. OK. So here's a claim that I will only intuitively show. The claim is, consider histories for which the belief states are unit basis. That is where all the probability is on one underlying state. How many such belief states can there be? N, because there are n underlying states. Now, such a belief state may never happen, but conceptually you can consider it, right? You can consider starting in that state and knowing that. And then there are n rows, n histories that correspond to those belief states. The claim is any row, any history has a corresponding belief state. And so let's say, look at this row H2. This has a corresponding belief state B of H sub 2. The claim is this row is the weighted combination of those n unit basis belief states with the weights corresponding to the belief state. In other words, all rows are linear combinations, in fact, a very particular linear combination of the rows corresponding to unit basis belief states. That is, if you look at the prediction you would get, infinite prediction row you would get for starting in state 1, in state 2, in state 3, in state 4, in state n, then if you give me a belief state, which is a distribution over those states, then the predictions for that, because of the linearity, comes out as that belief state combination of those rows. So if there were 2 states, and a belief state was 0.8 times 0.8 probability of first state and 0.2 probability of second state, then it'll be 0.8 times the row corresponding to the belief state that has all mass on state 1, plus 0.2 times the row corresponding to where all the mass is on state 2, which means that the maximal rank is n. And it's again just linearity of the predictions. The predictions are linear functions of belief state. The belief state update has a normalization term, but the predictions are just linear functions of belief state. Okay. So every POMDP with n nominal states, underlying states, is a dynamical system of linear dimension at most n. It could be smaller than n. In fact, it turns out it can be arbitrarily smaller than n. But it's also true that to get that, you have to make pretty contrived situations to make it arbitrarily smaller than n. So there's a construction proof, but I'm not going to present it. Okay, so now I'm going to show you, well, I just said this. There exist dynamical systems of finite linear dimension that cannot be modeled by any finite nominal state, POMD, but I'm not going to show you that. Okay, now let's show you PSRs. So how do PSRs work? I still haven't shown you exactly how PSRs work. So now I'm having shown you that interesting systems have reasonable rank. And we're now going to show you how to model a rank n linear dimension rank, or rank n or linear dimension n system with n predictions, with n core tests, with the predictions of n core tests. So here are those n core tests. Q1 to Qn. I core test Q1 to Qn. State representation is the predictions of this vector Q, right? These. We already talked about why it's a sufficient statistic of history. Talked about this. Now let me show you how to maintain this state. That is, what are the model parameters? That is, I was in some history h. I had these n numbers, which is P of Q given h. Now I took an action A, saw an observation O. How do I update these numbers? That's the question. If I can update it, I'm done. I'm maintaining state, and I have a model. So here's the idea. Notice, let's look at one particular number here. Say P of Qi given HAO. Yikes. P of Qi given HAO. Well, just by it's the prediction for Qi given HAO, and just by standard probability, it's the one-step extended prediction, AOQI given the old history, divided by the one-step prediction given the history. Now notice that P of Q given H was a sufficient statistic of history. So I can make this prediction by some weight vector MAOQI. And I can make this prediction by some vector MAO. Question is, how many weight vectors do I need to keep as my model parameters? Model parameters, by the way, in an MDP correspond to transition, in a POMDP, correspond to transition probabilities and observation probabilities. So what are the parameters here? It's basically this set. For every core test Qi, and there are n of them, and for every action observation pair, I have to keep a vector, MAOQI, and for every one-step action observation pair, I have to keep this vector. So learning a model means learning these numbers, these set of numbers. Notice, by the way, these m's can have negative entries, because when you talk about rank of a matrix, you're not requiring positive combinations, just requiring any linear combination. And basically, therein lies the power of PSRs and the difficulty of PSRs. Yes?
So I guess I'm a little confused. What does it mean to be talking about the probability of an action? I guess I assume that we get to choose.
Right. Sorry. Yeah, of course. This is shorthand. I should really say P is a prediction. So P of AO. Nope. I have not started yet. Source select document cameras. So P of AO given H is probability of O given HA. Yeah, so just, sorry, it's confusing shorthand for prediction. So P's are predictions, but they translate to probabilities by conditioning on the actions. Because exactly as you said, the probabilities are, the actions are something under our control. By the way, you can do all this for uncontrolled settings as well. Okay. So this is just a pictorial representation of that. I don't know how it's a pictorial representation of that, but it is supposed to be that. Okay, so now every discrete time dynamical system of rank n or linear dimension n is a PSR with size n. So at least unstructured POMDPs, you don't lose anything in terms of size. You could gain something. All right. I'm going to ignore this. Okay, so here's a summary of where we are. K-history Markov models is a subset of K-nominal state POMDPs, which is a subset of K-test linear PSRs, which is equal to dynamical systems of linear dimension K. By the way, why do I call it linear dimension? Can anybody guess? The presumption is, the reason why I'm calling it linear dimension is that there is a alternative definition of nonlinear dimension that's different or smaller. Because I was requiring all predictions to be made linearly from the state representation. If you allow yourself nonlinear predictions, you could get a much smaller dimension of a system than the linear dimension. So linear dimension is the dimension that allows you to make all predictions linearly. But if you allow yourself nonlinear predictions, then you can have a much smaller dimension. And that's where you can imagine the opportunity for structure would lie, right? We would think about structure and nonlinear predictions and exponential family predictions and so on. So that's where we've gone, but I won't get a chance to get there. Okay, what I want to show you, let me remind you why we're doing this. We're doing this because there could be a latent variable representation that says I have some probability that there's a wallet in my pocket. So there's an object called wallet. I put it in my pocket in the morning when I got out of my office. I can't feel it right now. But I maintain a belief state over the probability that I have money on me. Or I could say I have a prediction that if I put my hand in my pocket, I'll feel something. I'll feel that particular something. Right? So those are two different ways of thinking about it. The nice thing about this, of making a prediction about ways of behaving, is that I can test it. I can verify it. While there is no such thing as a wallet, I would argue. But we won't get into this philosophical debate. I don't think there are objects. But that's a different debate. There are people who would think this is completely absurd, that thinking there are no objects. But there's a reason it's not clear to me why it's useful to think in terms of objects. It's certainly useful in physics, in language. It's certainly part of our language. It's not clear to me that it's a good representation for intelligence. But it's certainly there in our language. Okay, so PSR models, because they make predictions about things you can actually see as representations of state, rather than distributions over latent variables that you never get to see, at least in principle, afford the possibility to build more robust models. Notice, by the way, that very few communities learn latent variable models. So let me unpack that statement, because you might be surprised by my saying that. So there is no graphical model that I can just put on a robot, let it go about, and it will go about learning the model of its world. There is no such technology. Now, PSRs can't do that either yet. Now, you might be thinking, well, graphical models used all the time. True. Much of it is not learned. Much of it is somebody sits down and very thoughtfully and carefully writes down a graphical model. Maybe there are a few parameters that are learned from data. Maybe. Basically because you have to do EM, and EM sucks. You might have not heard that before, but EM is terrible. If you ever try to do EM, and you're not an expert, if you're Michael Jordan or Andrew Ng or somebody who does EM in their sleep, that's a different story. But if you try to do EM on a real problem, it doesn't work. Not that PSRs are a silver bullet at this point. But the reason why they don't work is because, or one of the reasons, first of all, there are local minima issues, but part of it is because you have to do this expectation max, because you're doing latent variables. It's not clear to me we need latent variables. This is an argument against latent variables. Now, you can argue you can use both latent variables and these sorts of predictions, and surely that's true. Okay, but let me give you the foundational algorithm for learning PSR, just the basic starting point. Right? You have to be much cleverer than this. I'm running out of steam. I'm not going to show you an example. I'm just going to show you very quickly two things, discovery and learning. I apologize for bailing out. I spent hours in the bathroom yesterday, so I want to just sit down somewhere. There are two problems that arise when we want to learn PSRs from data. One problem is, what are the core tests? The core tests, that problem of discovering the core test, we call the discovery problem. Then there's a problem of learning the parameters. And of course, these two problems have their counterpart in the latent variable setting, right? Because you have to decide how many latent variables there are. And then you have to learn the models of the latent variable models. Okay, so let's look at this discovery and learning question. Let me show you it this way. Imagine we get some experience in the world, and we start building out the empirical matrix that corresponds to the system dynamics matrix. So we consider all one-step tests and all length 0 and 1 histories and build out that part of the matrix. And we compute its rank. Now, that's not the rank of the full matrix. Well, let's expand. Let's do length 2 tests and length 2 histories. And let's compute the rank of this matrix. And let's keep doing this until the rank doesn't change. I wish I could say that that's a guaranteed way of solving the discovery problem. Turns out it isn't. In worst case, you can have successive steps in which the rank doesn't change and then changes later. But for most applications, it's not an issue. Notice, by the way, another perspective that I should say to you that Jeff Gordon has been pursuing in particular. Another way to build a PSR is to just populate this matrix with as much data as you have. So you've got some data. Obviously, you can make more accurate predictions for shorter tests and shorter histories than longer tests and longer histories. But just populate this matrix. And then any method for compressing this matrix is a method for learning a PSR. So dimensionality reduction approaches, all of that sort of stuff can be used for PSRs, and is being very fruitfully exploited by Jeff Gordon and Brian Boots. In particular, they've gone towards linear dynamical systems and continuous systems, but anyway, but there's this quite good idea. Okay, let me now show you learning. Nope, I'm not going to show you learning. Here's how I'm going to show you learning. Suppose now I have the core tests. I've done the discovery part. So now what do? Here's how I do the parameters. The parameters are these M vectors. What do the M vectors do? They take my core tests and transform them into predictions of one-step extended tests. I can populate this from the data. I can populate this from the data. And I can do inversion to find this matrix. So linear inversion, matrix inversion, matrix inversion can solve for the for the parameters. Because remember why? Because there is a meaning to these M vectors. MAOT1, where these are a test now. Unfortunately, I've called them T's rather than Q's. Think of them as Q's. So it'll be Q1, Q2 to Qn. This vector is the vector that takes a prediction, makes the prediction for AO, for that extension. And so you just get that from the data, and it turns out you can do it through matrix. Guaranteed, if you had the true numbers, it'd be guaranteed to be linearly invertible. Of course, you have estimates, so you have to be more careful. But you can just do it by careful matrix inversion. I'm going to stop. Ask questions if you want. Let me say a few summary things. Where has this gone? We've done some nonlinear PSRs. We've done some, brought the idea of exponential family, max entropy-like things into this. We've gone down the road of doing Jeff Gordon has gone down the road of doing some dimensionality reduction. One of my students did a thesis on common filter-like systems and showing that you can do the common filter system in this sort of way. Turns out there's an old idea that did it this way called, what is it called? The name is on the tip of my tongue. The name for the PSR version of common filters is on the tip of my tongue, but I'm not going to remember it. Sorry? State space ID systems. No. There's methods that were developed that because of the PSR work, Jeff Gordon and Brian have revived and shown that, in fact, it can be much better. Now, of course, PSRs are not useful for applications where the latent variables are the variables you're interested in. So if you're interested in topics in the latent variable of what topic a document has, then this is not the right model. If you're interested in predicting what string will come after you've seen a partial string in the document, this could be a right model. Right? This is saying the goal of a model is prediction. Often, in many applications of latent variable models, the goal is the latent variables. Right? I want to build a topic model. I want to get a probability distribution over topics. It's not clear to me that that's what they really want, but that's what they say they really want, for a while anyway. I think that's a mistake, but that's a different discussion. Yes?
So obviously HMMs, POMDPs, and whatnot are used all over the place.
Yeah.
Are you saying people are missing the boat?
I don't know. I don't know. I know that Jeff... Yes, so that certainly I'm saying. Jeff Gordon in particular has taken that pretty seriously and pushed in the direction of robotics. Robotics is the area where I think it has the biggest potential, mainly because I think in text processing and so on, so much engineering has already happened through thousands of person-years of engineering effort that to outperform it using a more tabula rasa method is going to be extremely difficult. So the challenge, it's a sociological challenge, right? You'll only be interested in text processing if you can beat some system's performance. The problem is those systems are the result of thousands of person-years of effort, while we're doing 4 years of effort, person-years of effort. See, so where is their better chance of showing this off is robotics, where they don't have engineered models that work on an arbitrary robot in an arbitrary environment. So that's the challenge. Should you do speech this way? Maybe, but literally huge amount of effort has been put into engineering HMMs for speech. But I'm not interested in speech, right, per se. I'm interested in the flexible AI question, which is how do we build models about the world? And I suspect that these latent variable models are going to be less robust. they lead to knowledge engineering, and knowledge engineering is dangerous from the point of view of flexibility. But that's a philosophical debate. If you want to see an application of PSR on the most cutting edge thing, go to Brian Booth's web page. He's doing a thesis on this topic, and you'll see it. You'll see some applications. Any questions? I mean, you can probably tell that my way of thinking about things is often quite contrarian to most people in terms of, I'm interested in where rewards come from. Most of the world doesn't worry about it. I'm thinking about predictions of state, not the way most of the world thinks about it. I have a couple of students here. I probably shouldn't be saying this. They might scare them off. But it's a view that sort of says, I will take a minute. Now, this is being recorded. I probably shouldn't be saying this. But I think there is an overemphasis on linguistically inspired representations in AI in general. And this is a pushback on that style of thinking. It's not clear to me that you can't use history, that you shouldn't use history, that you shouldn't use latent variables. Maybe you should. Maybe it's a mix of things. But certainly, so here's a one-sentence summary of what I have actually just shown you. I've shown you that predictions of short-term future capture arbitrary past in history. What I've shown you, I've really only literally formally shown you one thing. Predictions of short-term future capture information arbitrarily far back in history. And furthermore, I've shown you a small number of predictions of short-term future can capture rich information about history. POMDPs also can capture information arbitrarily far back in history, right? That's the difference between a POMDP or an HMM from a K-order Markov model. So that's the direct competition. Okay, let's stop. By the way, if there are questions you need to ask or want to ask and don't get to catch me, send me email. I'm always looking for new students. If any of you want to desert your current advisor and want to work on reinforcement learning, write to me.